Good morning, everybody.
Good morning.
I'm going to send the full sheet around again, just check that off. The 2A students are very, very nervous. They have their first exam this Thursday.
Oh, the babies.
Yeah, so be nice to them.
No.
Yes, yes, be nice to them, right? Especially next Thursday if you're standing out there and they're coming out, right? Just reassure them it's going to be okay.
Give them some applause.
If you don't be noisy, right?
Quiet.
Unless the exam's over.
Golf clap.
That's all fine and good, but you're like, well, who's holding my hand, Mr. Balogh? I'm in physics 2B. Okay, I left you with some terrible puns last time. So let's just review real quickly, right? Okay. What's this?
Wait, we can't see it.
Blank screen.
It's a dark screen.
Can you just pretend that you can see it?
Are they more puns?
No, it wasn't more pun. It was actual physics, but I've got to reboot the thing. Where is it? Done something new. It's like totally disappeared now.
Point charge versus coulombs. Oh, like a dome. Yeah.
I was hoping I can bring it back. Okay, all right, come back online. No tech problem too big. Let's see. All right. What's that? Ohm's law. Okay. Critically, the relationship between what two things? Voltage and current. Okay. The resistance here is the constant is a strong word. Is the thing of proportionality that relates voltage and current to each other. Now, resistance itself does depend on the physical attributes of the thing that the current's flowing through. So the resistivity rho, again, is set by the material. It's different for different metals. The length of the wire, if you want to think of a wire, right? And then the cross-sectional area of the wire. So I want to show you some videos that highlight what happens with resistance, and some of these clips are going to introduce an idea that is like elevation, like batteries are pumping charges up and resistors are like staircases coming down. It's a good analogy to have in your brain for what's going on inside of an electrical circuit.
To make a current flow through a conducting material, a voltage is needed.
So that's a battery symbol over
Current
there.
is always proportional to the voltage. The constant of proportionality is called the resistance. This equation is known as Ohm's law. An element in an electric circuit with resistance is called a resistor.
But do you see how like the battery is like a elevator or an escalator heading up? Right? They've tried to make this look 3D, right? And then so the battery pumps charges up, and then the charges fall down the stairs, losing their potential, right? And then they circle back to the battery, which pumps them back up. then the charges go down. There's lots of different analogies out there. I've heard like water pumps and waterfalls is another good one, right? But the idea of a battery is that it's going to give charges potential. And then a resistor is anything in that circuit that is going to use that potential to do something. Right? A light bulb lights up. A washing machine washes clothes. Cell phones, right? Like it just, whatever is using electric potential to cause work to happen. So where we come into contact with this most on sort of an everyday basis is in our devices and in our homes. And especially with how electricity gets to our homes and the power grid and things like that. So I want to show you the effect that resistance has on wires.
Under the influence of an electric field, electrons move through a metal much as a marble falls through a viscous fluid. If it weren't for resistance, they would accelerate freely, like a falling body in a vacuum. But as it is, they move on the average at a constant speed. Resistivity is like viscosity. The more of it a material has, the slower a particle will move through it.
Which one of those has the least resistance? The blue one, right? Okay, you saw how easy it was for that marble to flow through? So in a similar vein, electrons moving through wires can either have an easy time or a hard time, right? So resistivity, that rho that's sitting in front of the L and the A, right? That's what's determining how fast a charge can move through it. Now, of course we know it's the electrons that are doing the moving. But in an electrical circuit, we're going to treat positive charges as flowing through the circuit, right? Using that charged model.
Have you ever seen your house lights dim when you turned on a heater or a heavy appliance? We'll use this model of house wiring to demonstrate the effect. 2 resistance wires will substitute for the normal copper wires used in a house to increase the effect. They run ordinary household current into this bank of lamps and heaters, which can be switched on and off individually. We'll first switch on the lamps. Then heaters will be switched on one at a time. When enough heaters are added to the line, the lamps dim. The electrical energy lost in the wires which deliver the current is dissipated as heat.
So what does resistance do in a wire? Causes it to heat up. It's like friction causes things to heat up, right? When you stop your car, where did all the energy go? It went into the brake discs and pads and slowing your car down, right? It got turned into heat. In electrical circuits, resistance does the same thing. How do you stop this from happening in your house? Yeah, don't turn everything on all at once. So, I won't ask this question, but I'm sure some of you were confused about like your house lights dimming when you turn something on. If your house has a bunch of LED bulbs in it, this probably doesn't happen anymore. Okay? LEDs are really good at buffering the changes in electrical. But under the old incandescent light bulbs, if you turned on, say, a vacuum cleaner or something like that, you'd see the lights dim in the house. Okay? And some of you were like, yeah, that still happens. And it kind of depends on, but the way that you don't burn your house down, okay, is with circuit breakers. And we'll get more into household circuits here in a little bit when we start talking about circuits specifically. But there are circuit breakers and building codes, and the building codes specify how thick the wires need to be for certain circuits in your house. If you have like an electric dryer that's running on a much higher voltage, much higher current, that has to be a thicker wire than, say, the wires that are in the wall for a normal plug. And the building codes make sure that those wires, what's a thicker wire do for the resistance? Where is the area in that equation? It's in the denominator, right? So the wider we make the wire, the bigger we're making the cross-sectional area. What's happening to the resistance? It's going down, right? Okay. But then you have to also have a certain amount of length of wire running through the wall to the switches and all that kind of stuff, right? So that increases resistance. So the building codes are a quick way for electricians to know, okay, this is the safe kind of wire to stick for this kind of electrical circuit. And they're specified to not heat up past a certain point, given a certain amount of current, which is why the circuit breakers will trip if like you try to run the coffee maker and the hair dryer and all the appliances at the same time. You'll overload the circuit will trip. It's tripping before it ever gets to the point where those wires are gonna cause a fire. Okay, so let's do a quiz. And since we are here and we're playing with current, and there are weird things in these physics video clips that I've got, I just have to show you what's next to it. I mean, come on, if you have current and a hot dog, what are you gonna do?
We'll screw this hot rod under two nails and run a current through it to show the heating produced by the current. 110 volts are applied to the nails, and a current begins to flow through the hot dog.
It's a standard household current.
After a few minutes, the hot dog begins to steam from the heat produced by the current.
Are hot dogs conductors? Yes. Right? Do the hot dogs have resistance? Yes. Right, okay. And that resistance is enough. Is this a good idea for the Science and Engineering Club fundraiser?
Yes.
Cook hot dogs with electricity and serve them? This is not a good idea. This is not, you guys are weird. You guys are weird. It's not nearly as good as pickles though.
We'll use this pickle and two nails to show the usual type of electrical discharge. The nails are inserted in the ends of the pickle, and electrical leads are connected to the nails. When we put a high voltage across the nails, the pickle lights up at one end.
Oh, a conductor, definitely. Especially because there's a bunch of salty water and acidic water inside that pickle, okay? But why did it light up at one end? We need a chemist. Basically it was the sodium and other salts that are in the pickling juice, okay? Ionizing, getting stripped of their electrons, right? It happens at like one end of the pickle too. It doesn't happen at both ends of the pickle.
Why?
It's just, I don't know. It's a chemistry thing. Why do chemicals chemical? Because they do, right? Like it's just, yeah, right? Okay, so let's transition away from that. I know, it is fun. It is fun. And talk about electrical power. So, back in the dawn of time in physics 2A, right? Okay. We did talk about power. Does anybody remember sort of the generic definition of power? It was work per time. It was this expenditure of joules, energy per time, right? And so, electrically speaking, right? So I'll just write it out. Energy per time, right? In terms of like electrical energy, do you remember what electrical energy is? We kind of defined it in terms of like voltage and charge. Remember we said voltage was the electric potential energy divided by charge? So we can find the energy, which is in joules, right? By multiplying a charge times a voltage. So our power is going to be Q, we'll do delta Q, some amount of charge is changing, times some amount of voltage divided by some amount of time. And what is a change in charge over time? When you count the number of charges flowing down a wire per time, what's that called? Current. So power is current times voltage. So just like power is work per time or energy per time in 2A, electrically speaking, it's current times voltage, or at least that's one way to talk about electrical power. You already know the unit for power. In fact, you don't even need to remember it from physics 2A, because this is the unit that you'll see on light bulbs.
Oh, wow.
Watts. And it seemed kind of weird back in 2A when we were talking about power. I was talking about watts. And remember when I talked about horsepower? We went and ran up the stairs and all that, okay. But it felt weird to be talking about like the wattage of a human being. It was, horsepower or something like that, horsepower of a car. But watts is the standard unit of power, and it's the unit that we associate mostly with electrical power, right? Okay. So, and a watt is a what? Is a joule per second, which also happens to be a amp times a volt. Give up on the units, just believe, right? Stay in standard units and you will be okay. Especially when we throw Ohm's law into the mix. Because if we throw Ohm's law into the mix and we substitute in for this potential right here, then another way to write power is I squared times R. Now this is often, for reasons that we'll talk about in a minute, or later, this is called the power lost equation. And at the risk of causing some mental trauma, I can rearrange Ohm's law so that the current is the voltage divided by the resistance. And then I can throw the current in there. And what do I get now? V squared over R. I can box that equation down there. And it can be useful. But I want to warn you about something. Is the power directly related to or inversely related to the resistance? It's directly related in this equation and inversely related in this equation. Here's the trap. It's not. Okay? Does resistance cause more power usage or loss? Yes. But these equations suggest it can be directly or inversely related to the resistance. What these equations are kind of hiding is what's being held constant. Okay? So feel free, it's perfectly valid. If you know the voltage and the resistance, you can calculate the power. If you know the current and the resistance, you can calculate the power. But don't try to think of, okay, does the power go as the resistance? Power, more importantly, goes as current squared and voltage squared. Do you see that? Right? Power is more influenced by current and voltage than it is by resistance. Resistance is in there because resistance tells us how voltage and current are related to each other, right? But the two in the boxes are the ones that are most often used. Okay? So, I've had lots of questions over the years. Mr. Balogh, the resistance is both. I'm like, I know it's both. Don't think about the resistance in terms of power. Think about current, think about voltage, and you'll be all right. Okay, so there's another term that most people that pay their electrical bill are familiar with. Okay? And when PG&E charges you for, okay, so PG&E, are they a power company or an energy company? What are they charging you for? What's on your bill? How much you're using and what unit do they give? A kilowatt hour, good. Okay? The meter on the side of your house is keeping track of a unit called a kilowatt hour. That is not a kilowatt per hour, it's literally a kilowatt times an hour. So what's a kilowatt? It's 1,000 watts. So let's say that you have a 100 watt light bulb, okay? How many kilowatts is a 100 watt light bulb? 0.1, okay? Let's say that you run your 100 watt light bulb for an hour. It would be 0.1 kilowatt hours of usage. But again, my question stands. Is that power or energy? A watt. What is that a unit of? That's power. And hours, what is that a unit of? Time. What happens when you multiply power times time? You get energy. PG&E is charging you for the energy that you consume. The energy you consume depends on the power of the things that you are using. Your microwave probably runs on about 1,000 watts. Some are bigger, some are smaller, but on average 1,000 watts of energy. So, how many kilowatts is 1,000 watts? 1. If you run your microwave for an hour, don't do this. But if you run your microwave constantly for an hour, how many kilowatt hours is that? 1 kilowatt hour.
So why is it not kilowatt per hour then?
Because they're charging you, for the energy you consume. They're an energy company, not a power company. It's important to understand that you're being charged for energy, especially in the context of how much does it cost. So this is an older version of a PG&E bill. Like most people don't even look at these things anymore because it just comes via the email or the bank account or whatever, right? Okay, they just take it from you. But if you actually dig in and you start looking on the website, and I've redacted some information from this. I wasn't gonna pull up my personal account number and all that kind of stuff, right? Okay, but this is an actual bill. You can see from 2009. Okay, because the new PDF version of the thing you can download is just, it's messy, okay? But there's a lot of numbers on here. But do you see how December 7th through December 31st, how many kilowatt hours did the Balogh household use? 307.5, right? And you can see there, kilowatt hour, like it's time, it's all multiplied together, right? Okay, okay. So back then in 2009, it looked like, okay, wait a second. The Balogh household did not use 307. The Balogh household used more. See how confusing this is? My baseline quantity was 307.5. The baseline quantity is what PG&E and the legislature of the state of California determine you're allowed to use for a certain time period. Did you know that you were allowed only a certain amount of energy per month?
Charge if you go past it.
If you go past that number, they can charge you more. So in the Balogh household, we used up our baseline quantity. And look, baseline quantity back then was 11 cents per kilowatt hour, 0.1135, right, okay? And then because we went over, it looks like we went over by like 102, okay? The 92.25 was, they were charging us 13 cents per kilowatt hour. And then we went 10 kilowatt hours over even that. These are called tiers, by the way, okay? We went into tier 3, okay? And look, it went from 11 to 13 to 26 cents per kilowatt hour. Back then, there were 5 tiers. And in the 5th tier, they were charging $1 per kilowatt hour, okay? So this is a system that's in place to encourage conservation of energy, right? And so that If you don't go over your baseline, which everybody does, by the way, okay, right in Fresno, because we have air conditioners. If you don't go over your baseline, then you won't be paying as much. If you go over your baseline, you pay a lot. Nowadays, there's only 3 tiers. Those, and you are charged a different amount depending on the time of day. The price of electricity now fluctuates every 5 minutes. By law, they have to report that, so there are websites you can go to see the live amount that they're charging per kilowatt hour, right? But it fluctuates based on market demand and time of day and all that kind of stuff, right? So it's got even harder to figure out what your electrical energy usage is going to be. Predicting it's harder than actually seeing it after the fact. But that's, okay, so they charged me $50.26 for using all that stuff, fine and good, okay, right? And then there's the following components. Generation, what does that mean? They're charging me for generation. Like, what is that? Generation. 21 bucks. 22 bucks they charge me. Making the electricity. That makes sense, right? I should be paying PG&E for them to run the dams and the gas stations and the solar power, right? They're making electricity, right? So yeah, I'll pay them for that. Transmission. $4. What is that with transmission? Getting it to me? Oh yeah, okay, infrastructure, I get that. That seems reasonable. Distribute, 15 bucks! What's transmission I get it to me. Distribution? That's like sharing with my neighbors. Right? Because it's got to get to the neighborhood, right? Okay, fine. Public purpose programs. I had to call on this one. I was like, what is this charge that I'm being charged? And the person on the end of the phone paused. And I wish I could have seen her face, right? Because I think the face fell and she sighed. And she said, do you know that fluffy hat mascot guy that goes to the kids' schools and tells them how good PG&E is? PG&E had a mascot back then that was like a big hat with legs. You never seen that? Oh yeah, no, it's hilarious. You know, like we have the Ram and all that kind of stuff, and it's the mascot suit. It was a big hard hat with legs. So yeah, I paid $2 for him to go to schools, fine, whatever. Nuclear decommissioning? 12 cents!
Nightmare fuel.
Okay.
Sorry, I Googled it.
You Google it? Yeah, it's back, right? Okay. I asked what the DWR bond charge was, and that's Department of Water Resources, something about water. Ongoing CTC, I gave up trying to understand at that point. Energy cost recovery amount, PG&E didn't charge me enough, so they wanted to recover. I don't know, right? Okay. But the point is, right, that you can go in and you can look and see what all this is. To simplify, what should you be doing? Yeah, not using electricity, right? Okay? You should not be using electricity. So let's do some calculations. Let's do some calculations on how much it costs, right? Based on some assumptions for just running some things. And then we're going to talk about energy vampires. And you're going to go home and you're going to become a crusader against energy vampires, okay? You're going to have your sharpened wooden sticks. We're going to go get them, okay? So, how do we calculate the resistance of this vacuum cleaner if we know its voltage and its current? Meditate on it for a little bit. What are we going to reach for? What relates current, voltage, and resistance? Ohm's law. Right? Solve for the resistance. Voltage over current. The voltage 120 volts. The current is 12 amps. What's a volt per amp? I don't care. I'm solving for resistance. So this is going to be, is that 100? 10? What is that? What's 120? That's 10, isn't it?
Yes.
Okay, 10 ohms. Was the math hard here? No. Okay, the math is not hard, right? It's getting the pieces put together and coming to grips with these units are weird, right? So again, standard units in equals standard units out, just believe, okay? How much power did this vacuum cleaner use? What's at my disposal for calculating power? I can do current times voltage. I can do current squared times resistance. I can do voltage squared but divided by resistance. The answer should be the same no matter what, so we'll just do the first one. Current is 12 amps. The voltage is that 1440? 12 times 12 is 144. And got an extra zero, a couple zeros in there, whatever. Right? Okay. So that is 1.44 kilowatts, isn't it? So if you run this vacuum cleaner for an hour, that's 1.44 kilowatts of electrical power. Energy. See, I made the mistake too. That's been used. All right, so let's do another one. Okay. So here we have a 100-watt light bulb running 8 hours a day for a month. We're going to calculate how much it costs to run this light bulb. Assuming 8 hours a day of usage, which 8 hours a day of usage, like you come home after work, 5, 6, whatever, right? You turn the lights on, they're on till midnight, 1 o'clock, 2 o'clock, doing your physics homework, crying into Wiley Plus, right? So right there, they've already been on for like 6 to 8 hours, right? And then you wake up, you turn the lights on, and it's dark in the wintertime, right? 8 hours might even be short, right, for when light bulbs are. And how many of you are in a household where the lights like don't ever seem to go off? Like I come downstairs and the lights are on. And I know nobody's been downstairs for 8 hours. So like what is going on? Right? Those photons gave their lives for nobody. I'm such a dad. Anyway, 8 hours a day for 1 month, right? 100-watt light bulb. Okay, there we're assuming 14 cents per kilowatt hour, which is it's like 21. Baseline I think is 21, 23 cents per kilowatt hour. Again, it fluctuates every 5 minutes. So let's see here. We've got to find out the total number of kilowatt hours that this light bulb has used up. How long is 1 month? 30 days? What did I do? I did 30 days. We'll call it 30 days on average, okay? So we know 100 watts is 0.1 kilowatts, right? So to find the total number of kilowatt hours, I need to find the total hours that this light bulb was on. So how do I find the total number of hours this light bulb was on? 8 hours per day for 30 days, right? So the days cancel, so 8 times 30 is 24, 240? 240 hours, right? And so then I multiply, right, by, to get the kilowatt times hours, I have to take my kilowatts, 0.1, and I have to multiply by my time, 240, so that's 24 kilowatt, not per hour, kilowatt times hours. So now, by taking the power of the bulb and how long the bulb was on in that 30-day time span, I've been able to find the total amount of energy, right? A kilowatt times an hour is a unit of energy. It's not a joule, it's just another way of talking about things like joules, right? So I know my electrical energy, and I also know how much it costs per kilowatt hour. So I have 24 kilowatt hours, and for every 1 kilowatt hour, it's or I'll just do 14 cents. I will do $0.14. Okay? And we'll get the answer in dollars here. So I take the 24, multiply by the cost per kilowatt hour, and I got, $3.36. for running my light bulb? Well, no, but that doesn't seem so bad, right? That's one light bulb. How many light bulbs are there in your house?
So many.
Okay, right, okay. Now, a 100-watt light bulb, this would have been an old-fashioned incandescent light bulb with the film in it and all that kind of stuff. The same amount of photons coming out, same amount of light intensity coming out in an LED light bulb, you can actually get that down to about 8 watts.
8.
8.
Oh.
The 100-watt equivalents run anywhere from 8 to 12 watts, depending on the bulb manufacturer. Okay, so let's just round this off, and let's say that we got a let's say we got one that's runs at 10 watts, right? So we've taken the energy consumption and divided by 10, haven't we? So how much does this bulb now cost? 33 cents for the entire month. You see what happened there? Gains in efficiencies can really pay dividends in terms of the bottom line cost that you are going to pay. So you're going to go home, you're going to find all the light bulbs in your house that are not LEDs, and you're going to replace them with LEDs. And if you're like Mr. Balogh, I'm student, I'm poor. You are going, and if you're paying your own way, you got your own house, you're paying your own rent, right? Okay, you're not living with your parents, whatever. You are going to call PG&E. And you're going to say, I am a low-income student. What have you got for me? They will send out light bulbs. Okay, remember the public purpose programs? The fuzzy hat with legs? There's other elements to that for low-income households to get their energy efficiency up, energy usage down. Okay, so let's talk about energy vampires. I have here a list. It's a bit of an old list. This one's dated 2009. I have checked the data since. I really need to update my kilowatt hours, but it's hard with the amount that fluctuates now. But I have checked this list over the years, and it hasn't changed. Like percentage points, okay? But this document right here is a table. I actually just printed out the whole table of electrical energy use by classification of device. For example, a mobile phone charger. How many watts do you think a mobile phone charger uses while it's charging a phone? It depends. So some of you know the wattage of your charger. Maybe you have a fast charger that runs at 60 watts. Maybe you only have a 30-watt charger. Maybe you have a 5-watt charger with those little tiny bricks, right? It takes forever to charge your phone. The speed at which your phone will charge depends on the power that your phone can take, but also the power that your charger can put out, right? If you have a 60-watt versus a 30-watt, it's going to charge twice as fast, assuming the battery can take the 60 watts, okay? So that's going to change depending on your phone and the supply. But how much does one of those chargers, on average, how much power does it consume when the phone is plugged in and the phone is charged? So it's just sitting there. On average, 2.2 watts. Like, oh, well, that's not 30, right? When the brick is plugged in and the phone is not connected, anywhere from half a watt to 1 watt. Now, I would contend that with your phone plugged in, it's actually doing something. It's like maintaining the battery level on your phone, which is a good thing, right? But if the brick is just plugged into the wall and it's not connected to your phone, then all it's doing is generating heat. Go global warming. Let's just hit some your computer. So I'm gonna put a bunch of categories here together, right? So when your computer is on and doing something, like browsing the web, watching YouTube, doing something like that, on average, a laptop is going to be taking about 50 watts, and a desktop is going to be taking about 150 watts. Okay? Playing a video game, depends on the specs of your computer, that can go up to 300 to 400 watts. Okay? But here's the kicker. When you put your computer to sleep, your laptop asleep, so 50 watts while it's on doing something. When you close the lid, but it's plugged in, how much energy is it taking? On average, 15 watts. When the power supply is plugged into the wall all by itself, not connected to the computer, 5 watts. Television. Where are all the televisions? Even better. DVRs, like the cable box thing that sits right there. Okay, anybody have cable anymore? No. Satellite? No, we just all use YouTube. Okay. Right. But okay, game console, Xbox, PlayStation. Okay, all right. Now I'm hitting below the belt. Okay.
You already did that with PC.
No, because it's even worse with the Xboxes and PlayStations. While playing a game, about 100 watts. 100 to 150. They tend to be very efficient designs for the size and all that kind of stuff. When you push the off button on the game console, okay, when it's at idle, when you're not playing a game and you're just like at the menus, they take about 60 to 75 watts. Okay? When you hit the power button, any guesses? 60 watts. They don't turn off. Their sleep mode just turns off the display port to the TV. Why do they sit there? Running?
They like run updates in the background. So.
Bitcoin. No. It's because you probably told it, I want the latest update now.
Yeah.
And so it's sitting there going, update. Right? Just waiting. Okay? For an update to happen, and then it downloads the update, so you can be playing right away. Televisions. Okay? Big or small. Anywhere from, according to this, anywhere from 75 to 300 watts. Then it depends on the size of the television and all that kind of stuff, right? Okay, that's while it's on. When it's off, like you hit the remote and the screen go blank, on average, anywhere from 20 to 50 watts. What's an energy vampire? Something that sucks energy. You're like, oh, physics, Mr. Balogh, I know all about that, right? It sucks my energy all the time. An energy vampire is a device that when it is off, like you think you've turned it off or put it to sleep or whatever, your assumption is usually that it's gone off or it's gone to sleep and it's in some kind of low power mode. If a device that runs at 50 watts goes to sleep and it's got 15 to 20 watts of sleep power and it's not doing anything for you, how many devices do you have in your home that do this? Just about everything nowadays. Here's an experiment for you to run tonight. Go home, whatever, you're about to go to sleep, okay? And everybody else in the house is also asleep. What I want you to do is I want you to turn all the lights off in the house. And I want you to walk through every room that you're allowed to walk through. Don't walk into your right? Count the number of little LED lights that are shining back at you. I think you'll be shocked, especially in the living room. You'll turn the lights off, and you'll see a little tiny light maybe at the bottom of the television, and another one on the game console, and another one on the Switch, and another one on the Each one of those little LED lights is an energy vampire, waiting in the dark.
How do you fix it? Like, what's the solution? Surge protector that you click off?
That's exactly what I do.
Okay.
Yeah. In my house, the things that don't need to be, so there's some things that need to be on all the time. The refrigerator, right? The internet connection to my house does need to be on all the time because as far as I'm concerned, I could lose power and if I have internet, I'm good. Right? And it's been shown that people that don't have internet actually have much lower standards of living okay? So internet, like, I mean, it's not like water, if you don't have it, you're gonna die, but it's getting close. Because in my house, cell coverage is terrible. Like, I live in a black hole. I live in a Faraday cage. I have not been able to figure it out, okay? And if I need to get an emergency call out, it's going through Wi-Fi. I can't trust the cellular to work, okay? So to me, the internet, very important, okay, for safety reasons. But beyond the refrigerator and the air conditioner and the internet, okay, there's really nothing else that needs to be on, right? And so things that don't need to be on all the time have kill switches attached to them. The kill switch, it's a little bit like this, right? This one's fancy, it's got a bunch of switches on it, right? But if you plug everything in and dead. On, dead. And if it's switched off, it can't be a vampire. Lower your energy, kill the vampires. All right. See, did you think you were going to get practical advice about your house? What is this? Surprise face emoji. Sad emoji. So your house wires, okay? This is the ground plug, okay? And what do you think it connects to? It literally connects to the ground. If you go outside, you may not be able to see it, but there's, in your foundation or right outside the electrical box outside your house, there should be a wire that comes out of it and a metal stake that's driven into the ground. It literally connects to ground, okay? If it's not a metal stake, they might have attached it to the gas pipe or a water main pipe coming in or out. Pipes are perfectly good because pipes are mostly in the ground, right? So you have an electrical ground. And then there is a hot wire. That's the small eyeball. And then the teary eyeball, it's longer, right? Okay, is the neutral, right? And device manufacturers have come to expect, right, which side you're plugging stuff in. This is called a polarized plug. Polarized because most plugs nowadays, you can't reverse, right? There's one side of the plug that's like longer, it goes in the longer side, right? But there are still some devices. I had to go find an old soldering iron, and they kept saying, can we throw this out? I was like, no, it's one of the few things that has a non-polarized plug on it, right, okay? So that I can reverse it in and out of the socket. So let me show you what this thing does. Plug it in, okay, it's not on, okay, all right, now it's on. So this is just a soldering iron, okay? If I pull the switch, it lights up and it heats up the tip over here, okay? But that's not why I wanted to show you that. I've got this gizmo right here, okay? It turns on, beeps. This detects the presence of electrical power, okay? Not even just current flowing, but the fact that something is live, okay? So I can actually put this into, okay? And it will beep and it'll turn red to tell me that this is the side that's got the hot wire on it, right? So this detects, and I put it in the other side, nothing happens, but this is the hot side, right? It actually works by detecting changes in charge, so like I can get the static to set it off, right, by rubbing it on my clothes, right? But I want you to know something, right? If I hold this device onto the plastic like this, right, it's not detecting anything, even when I turn, like I turn it, so it does a momentary detection when I turn the power on, because there's a jump in current inside the device, that's what it's detecting, but it doesn't stay red, right? Okay, so now I'm going to reverse, because this is an unpolarized device, I can reverse it in the socket. Maybe. Reverse it, okay. I haven't hit the power button or anything. I gotta turn it on. What just happened? The outside of this thing, the plastic case of this thing, is now connected to the hot. What's the plastic case supposed to do?
Not do that.
Not do that, right? When it's plugged in correctly, the hot's on the inside, not the outside. So what is it possible to do with this?
Catch on fire. No.
I can shock myself now, right? Because the outside of this device is now hot. I hit the trigger, I'm still okay because I am electrically isolated, but if I were to step into a puddle of water or something like that, I very quickly could be a part of this circuit and have stuff, even with it not on, right? I could have electricity flowing through me. When we were doing electrical safety, we would talk about people doing the hula, okay? The hula is when you have connected yourself to a device and can't let go, okay? Because you're sitting there doing that as you're being shocked, okay? So how do you get around these unsafe devices? Well, first of all, you gotta make sure that your outlet is wired correctly, okay? This is why you hire electricians to come and do work for you, right? To make sure that they get them right. But since I trust nobody, I have these little devices. These are actually really, this is kind of expensive. This costs about like $20, $30 to get this detector right here. And you really don't need it unless you're really like trying to find wires and walls and stuff like that, okay? But these are easy. These cost like $2 to $5 depending on where you buy them, okay? And they've just got little LEDs on the end and a little chart that tells you, and all you gotta do is plug it in, okay? And I know you can't, so I cleaned this up way too fast. You just plug it in and it tells you whether or not something has been connected up correctly. What I really should do is break one of these, open it up and just get it all wrong everywhere. But I don't know if you can see the two orange lights that are on the end there. Two orange lights means that this thing is wired correctly. Okay? You plug this in here, oh, okay, it's wired correctly. You don't even have to take the plug apart, right? You can see here, this is a side view of the plug. They've got a ground wire, they've got the white wire coming in, which is the neutral, they've got a black wire, which is the hot. Don't trust the colors in your house, it could be different. But there are 9 different connections on the back of a standard outlet. If you do all the permutations for that, there are way too many ways for somebody to screw up hooking this thing up, okay? So I went through, and when I bought a house, I tested all the outlets in my house. Whenever I mess with an outlet, I retest it to make sure I've connected it back up correctly, right? But this thing will tell you if you have like an open ground. That means the ground isn't connected. Ground is very important. Hot and ground reversed. The ground's up there, and the hot is down there, and the ground's up there. That is very bad. That just means you're dead. Hot and neutral reversed again. Okay, we now have a case where polarized devices could think that you're safe, and then you're not safe, right? So on and so forth. So this thing can tell you whether. And I found 2 out of the 30 plugs in my house that were wired incorrectly. Okay? I think one of them had a faulty ground and the other one was wired incorrectly. So it's easy to do. I mean, even for licensed electricians, the design of these, the backs of these things make it very difficult. For other types of plugs you might see in your house, is like a dryer connection, something like that, okay? This is called a 240 volt plug. They're shaped a little bit differently, they tend to be bigger. So instead of going from 0 to 120, it goes from positive 120 to negative 120 for a total potential difference of 240 volts. They usually higher current circuits too. Now, as for the ground, okay, in a device like the one I showed you, this thing doesn't have a ground, right? And it also has a unpolarized plug, right? So it's possible to connect yourself to the hot side of this device, and then if there's enough potential for you to be connected through your feet to the ground, thus getting an electrical shock while using the device. If this thing had a ground wire in it, okay, the ground wire acts as the easiest path to ground. And so instead of you getting shocked in the event that there's a problem with the device, right, you end up connecting yourself, current flows maybe through your hand, but not through your body. You are not the quickest, shortest, least resistance path to ground. okay? That's what ground wires do. They help short circuits pass through wires rather than people. Just because you have a device that's not grounded doesn't mean it's not safe, right? It's better that there is a ground on it. But a lot of phone chargers, a lot of laptop bricks, they actually don't need ground in order to be safe. And that's because there's circuits in the charging bricks themselves that keep you safe and make it so you can't really connect yourself to any of that kind of stuff. A lot of kitchen appliances don't have grounds, and kitchens are a source of where water is. So these building codes require that there be something called a GCFI, a ground control fault interrupter, to check and make sure that there aren't excess currents and ground is working around water sources.
2 questions. First, if you stick a fork in the ground in one outlet, are you still gonna get shocked?
Nope. Okay, if for some reason the ground potential is very different from where you're standing, it's possible. But usually not. Usually your house is at ground everywhere. So.
And then second question, how come outlet shapes aren't standardized across like global?
Globally, it's because nobody can agree on what is the safest design for a plug. I'm personally a fan of what they have in the UK. I think the UK plug is amazing. Not only does it prevent somebody from like touching both sides while you're plugging it in, there's a fuse built right into the actual plug. So our plugs tend to be small and you can grab them with your fingers like this, right? But in the UK, they're bigger. And inside this thing, there is a fuse. And so if there's a problem with the device and you plug yourself in, the fuse will pop in the plug before it ever trips the, turns off the whole house. Again, I think is a fantastic design. Do you see how here the conductors go all the way into the plastic? In the UK design, the conductor is only at the very end tip and the rest is insulator. So even if you got your fingers onto the thing somehow, okay, you'd still have to you'd have to have your fingers inside the plug with the plug. It's impossible, right? So there's better ways to design these things. This is the design that somebody first came up with, and it's dumb. But it's standard for the United States. I just defined the United States, by the way. We're pretty dumb. We do some pretty amazing things, but we're also pretty dumb. What's this? Ah, it's a neuron! What do neurons do? What do you think process? Okay. Put a bunch of them together and you get Facebook. So the top part of this neuron would be maybe like where your brain is, right? Okay, and the dendrites of that neuron go off and connect to other neurons, and they all connect together to do stuff, right? And then you have is it the axon? I can't read that. The axon is like the part of the nerve cell, right? Okay, so you got this nucleus thingy up there, right? And then you got the axon, and it comes down to the nerve endings, right? Now, some neurons in the human bodies are a meter long. Like they go from the brain all the way down through the spinal column and into like your arms and your legs and stuff like that. Am I getting this right? Anatomy and physiology students, right? And so, why are we talking about it? These are the electrical wires of your body. When the nerve endings on the tips of your fingers go, ooh, hot, ooh, cold, ooh, touch, ooh, right? They have to send an electrical signal from the tips of your fingers into your brain. Sometimes. I burned all mine off cooking, right? But it's handled with currents and potentials all the way along that system. There's even built-in insulators in these nerve fibers. Is it called myelin? The myelin sheath? Oh, is it even written up there?
Yeah.
Oh, look at that, myelin sheath, right? I was going from memory. And multiple sclerosis is a degeneration of that insulating layer that's around the wire, and it causes all kinds of muscular problems in a person that has MS. So, the system is important to understand, but in a sense, it's Ohm's law. It's current, it's resistance, it's potential, It's power being transmitted. All that kind of stuff. Okay. Before we do series and parallel resistors, let's do a little bit of a, this isn't a side tangent, but it's more of a glossary for you. Because what we're going to do now is we're going to move into electrical circuits and circuit schematics and putting things together, seeing how current flows places, and eventually building up microwaves and cell phones and Instagram. So just a few symbols for you to be aware of in drawings that are going to be coming up, okay? So there are these symbols that we use to denote batteries, okay? This is my favorite symbol. It's the symbol that I use most often. It's the symbol I see used in a lot of online sources, but textbooks use a slightly different one. This is a battery. And this battery's positive terminal is the big side and its negative terminal is the small side. That's not always indicated. It's just inferred, implied, understood that a battery symbol in an electrical circuit will look like this. Now, there's another symbol very similar to this one that you already saw in one of the videos that I drew, okay? And it's basically the symbol kind of repeats itself. Small plate, big plate, small plate, big plate, small plate, big plate. Does anybody know where the term battery comes from? Okay. A battery back in the day so this is the late 1700s, early 1800s when Alessandro Volta was playing around with making batteries. A battery, have you ever heard the term like a battery of artillery? Okay. Battery was a word that referred to a collection of identical things. You have a battery of guns, a battery of cannons, a battery of artillery, a battery of fruit. Like if you had a bunch of barrels of apples, you could call that a battery of apples. It just was a word that meant I have a collected stuff. It's made in individual units, but they're all the same unit. And so when Alessandro Volta was sitting there putting layers of cloth and layers of metal and layers of cloth and dumping acid all over it, he had a battery of layers within his electrochemical cell. Well, electrochemical cell did not catch on. The battery did, right? Okay? So nowadays we think of a battery as a single thing that gives electrical power, right? But it referred to this idea that there were identical layers in this thing that caused chemistry to happen, right? And there was a battery of these layers, and so it later became known to be called a battery, which is why this symbol persists, right? It's cloth, metal, right? Positive, anode, cathode, all the way through, right? But usually we will use this symbol right here to denote the battery, okay? So I better label that here. Batteries. Okay. Other circuit elements we run into. We run into capacitors. The symbol for a capacitor is that. Unfortunately, when Mr. Balogh was going fast, trying to draw a circuit diagram, his batteries will look like this and his capacitors will look like this. Right? So if you're confused because I've drawn it wrong or confusingly, shoot your hand, Mr. Balogh, what is that? Okay? But generally the capacitor should have the same length on both sides. Okay? It's a representation, a pictorial representation of the parallel plates that exist inside of a capacitor. I usually label mine above with either the capacitance or the voltage for the battery. That way I can tell the difference. And then there is a resistor. You've probably seen this symbol before. Looks like a little sawtooth, squiggly something. Okay. Again, when Mr. Balogh is going fast, they tend to look like that. Right? But again, if you have questions, be sure to ask me. I'm not a good artist. So these are the symbols that we use to denote things in electrical circuits and is a big part of the visualization process that we're going to be going through as we write out our electrical circuits and try to apply Ohm's law over and over again. Okay, so series and parallel. There are two ways to hook things up to each other. Take two resistors, you can either put them one after the other like train cars, where the resistors, like the first resistor here, we'll call them R1, connects to the second resistor, R2. And this is a series connection because think of like a charge moving through these resistors. In order to get to the second resistor, it has to pass through the first resistor. Usually series and parallel don't mean much unless you are referring to them being connected to a battery. So all three of these resistors are in series with each other. Okay? That's different than parallel connection. In a parallel connection, R2, R3 connected to a battery, voltage, okay? There is a junction. So if I'm coming out of this battery down here and I come up, I get to a point where there's a fork in the road. I can either keep going straight up or I can turn to the right to get to R1. At that junction right there, a charge has to make a choice. Go one way or the other, right? That's how you tell when there is a parallel connection. Look for the junctions. Junctions give away that there's some kind of parallel relationship going on. The way that you tell the difference between series and parallel is you follow the flow. If there's no deviation, if there's only one way, that's a series connection. If there's a junction, parallel is happening somewhere. You got to try and go figure it out. So, as an example of this, put a battery right here, put a resistor right there, put a resistor right here, a resistor right here, there, we'll come back to this battery, okay? So we'll go 1, 2, 3, 4, 5. Can you identify for me two resistors that are in series? Like definitely in series. It's 4 and 5. 4 and 5 are the only ones that are definitely in series. And how can you tell? There's no deviation between them. You can walk from R4 to R5 and there's no junction. You see how I put a corner in it though? Right? There's a turn right here. That's still a single wire connecting these two resistors together, right? So I can walk from 4 to 5 without ever passing through a junction. So I know they're in series with each other. But what about R1? Is R1 in series with R4? No. Coming out of the battery, right, following the battery, I hit a junction and now all bets are off. Okay? There's going to be some kind of parallel relationship. Can you see two resistors that are definitely in parallel? R2 and R3 are definitely in parallel. Because there's junctions between them, right? Now, we cannot say that R1 and R5 are in series or in parallel yet. I'm going to teach you some rules about how to move through these circuit diagrams, but the learning starts with being able to definitely identify series and definitely identify parallel. The reason I can say R2 and R3 are in parallel with each other is because I have what amounts to exactly the same branch, top to bottom. So if we think of water flowing down these pipes, okay? The water splits up there, right? Some of it goes through R2, some of it goes through R3. So if I've got 10 units of water going in at the top, and R2 takes 2 units of water, how much is R3 going to take? 8. You have to keep the same amount of water, right? But then R3 and R2 come back and meet up, right? 2 meets up with 8 for a total of 10 again, right? I can look at the diagram and see that it split, but then that same split came back together at a point. I know that R2 and R3 are definitely in parallel. This is something you're going to need to practice a lot. I've only given you some homework problems, but at the end of the chapter, there's a lot of pictures. Even if you don't do the problem and you just look at the picture and practice, is this series, is this parallel? And there's going to be more rules on Thursday, okay, for identifying these things. I'll teach you that then. That practice is going to help you a lot. I will see you on Thursday, and we will finish up this chapter, because what happens next week? The exam.